The second type of commonly used pressure vessel would be the spherical pressure vessel. So as we take a look at this one, we can calculate out stresses in much the same way. So it doesn't matter where I cut this one because it's a sphere. So it's all going to be the exact same no matter where I cut it. And so what do I get? I get my computer wanting to get ahead of me. So the sum of the forces in the x direction will be 0. Well, I have stress 2. And why do I label it stress 2? Because it's the exact same as kind of the stress in the other one. Because as I look at this little element here, stress 1 and stress 2 are going to be the exact same. And so I am using stress 2 to be consistent with the longitudinal stress, and you'll see why here in a second. And if I look at it, I multiply that by my area, which is dA, 2 pi r times thickness will give me my area. I have the pressure going the other way. Pi r squared is the area. Once again, I finish this out. Stress 1 and stress 2 are the exact same. PR over 2T. So all of the stresses in a spherical pressure vessel are longitudinal stresses, and so they're going to be half of what the stresses are in a hoop stress direction. And so if I sit here and take a look at this, I can look at more circle for in-plane stress transformations, and it reduces all of it to a single point, which is just the stress at A. The second principal stress is going to be 0 because of the way that we put this together. And so what's going to be the maximum shear stress, though? Well, the maximum in-plane shear stress, we know if we rotate this 90 degrees, we'll get, if we rotate this 45 degrees, we'll get the maximum shear stress. And so that's going to be 1/2 what the principal stress is. So our maximum in-plane shear stress in a spherical case is going to be PR over 4T. So now, typically, let's talk about failure modes. So if a thin-walled pressure vessel, if the pressure is greater than the stress that can hold it together, so pressure in here is greater than pressure out there, it's going to explode. Yes, we're all familiar with that. We like to see things blow up. In fact, I should have found a video to put in here of one exploding. In fact, I just grabbed a 2-minute video that I'm going to upload with these lectures. That will show one exploding because that's what we all need at whatever time of day that you're watching this, is watching things explode. The one thing I did want to point out with this now, with pressure vessels, if the pressure on the outside is what's greater and causes it to fail. So if I got it coming in here and the pressure on the outside is much greater, it doesn't explode, but it will implode. It will crush on itself. And you would see this in a couple different cases, where if you had like storage tanks under the water, but where you would see this the most would be on like a submarine. Because basically a submarine is a cylindrical, thin-walled pressure vessel. And so as you watch movies, they talk about crush depth. That's how they calculate it out. They take this thin-walled theory and they figure out, well, hydrostatic pressure. How much hydrostatic pressure do we have to put onto the submarine to have it crush like a beer can? And then that's what they do. And so just think, when you take fluids, you'll be able to take that knowledge of hydrostatic pressures, apply stresses of thin-wall pressure vessels, and you will be able to know how far under the water you would have to put an empty beer can before it would crush. You'd have to seal off the other end, though.